Hey there, welcome back to your next lesson on high level mathematics. So we're continuing with geometry again, and this time we're looking at transformations, which are kind of like what you would think they are. So you take something like a shape and we're transforming it into some other shape. And we're looking at how we can mathematically quantify those transformations and what are those properties. And we can also look at transformations of graphs as well, because a graph is essentially like a shape, like a curvy line, one-dimensional shape essentially. And we're going to see how those transform as we sort of tweak the function that defines that graph. Um, so here we go. Here's our lesson plan for today. So we're going to look at, first of all, what are our different geometric transformations. So we learn a lot of keywords and what they mean, how they're applied. Then we're going to look at developing spatial reasoning skills. So this is like the ability to sort of close your eyes and visualize a shape and to be able to transform it in your mind. Could you imagine rotating it or flipping it or looking around and seeing it from a different perspective and things like that? Because that's something that doesn't always come easy to everyone, and we want to see how can we develop those skills. And again, we've got some more keywords we need to be aware of regarding that. Next, we're going to look at projections, which is like viewpoints. It's a matter of looking at, say, a three-dimensional shape from various viewpoints, and what would it look like from that viewpoint. Um, and then finally, transformations of graphs. How can we apply these concepts of transformations to then a mathematical equation, a function? So first of all, what are our transformations? So we're going to look at different keywords. So the first one is a translation, which is very straightforward, which is just simply something like this. When you move a shape, so you're not even changing the shape, you're just changing its position. So this will typically apply when you've got some kind of coordinate system. So we actually have you know quantified our positions, um, and then we want to quantify a translation. So how we typically do that is like, say if you just focus on a particular point. So we've got this point here at 1, 2, and if we move like this, it's moving to the point 6, 4. So we can see it's gone 5 across and 2 up. How do we encapsulate that information? We use something known as a vector. And near the end of this section on geometry, future lesson, we're going to look at vectors in more detail. But this is the vector fundamentally. You have these two brackets and these two numbers. 5, 2 basically means you're moving 5 to the right and 2 up. And so that allows us to quantify that translation. And so we could then, combine translations or, as well as other things. Notice here what we've created is essentially a right angle triangle. So if we wanted to, we could calculate that distance using Pythagoras' theorem. Also, if we wanted to do the reverse direction, so you see I've turned that arrow around, I wanted to go back, what would that look like? It would look like this. So here, that vector, it's the important thing about vectors. It's not just a distance, but it's also a direction. So we can have like 5 doesn't mean just a distance of 5. It means 5 to the right. So -5 means a distance of 5 to the left. And likewise with the y coordinate, 2 means a distance 2 upwards, -2 means a distance 2 downwards. So we do have negatives here because it's not just a distance, it's a direction as well. And we split up into a horizontal and vertical part. So that's a translation. Next up, scaling. So say if we have a three-dimensional shape like this, just a little cuboid, and then we have a bigger cuboid like this, and we think, okay, what is the scale factor? Scale factor typically refers to the lengths. So going from one to the next, how are the lengths scaling? Like what are we multiplying by? So when you're talking about scaling, you're talking about multiplication, not addition. So we've gone from 2 up to 4, we've gone from 1 up to 2. You can see there's a scale factor of 2 there. We've doubled all the lengths. Now, if we look at the surface area and volume of these two shapes, which we could quite easily work out now based on, what we've done in previous lessons, we can notice something like for a distance of that is scaling by a factor of 2, what you'll notice is that the area scales by a factor of 2 squared, and the volume will scale by a factor of 8, which might be obvious, really, because you think about area as basically distance times distance, isn't it? So if distance scales by 2, area will scale by 2 times 2. And volume is distance times distance times distance. So volume will scale by a factor of 2 times 2 times 2. So depending on the scale factor of the distance, we can then determine how the area and volume is going to change. So now you see here where we've not just scaled the shape up, but we've moved it. Like if we scale the shape up by just expanding from its center, it would do something like this. But it's not only scaled up, but it's moved. And the reason for that is because it's like we're scaling from a particular point, and we can determine what that point is by lining up, like drawing a line connecting the vertices of these two shapes. So if we have a coordinate system like this, so we want to find what that point is, um, we could draw the lines like this, and we find this is then the point. And this point is what's known as the center of enlargement. So what we're doing is we're so sometimes you might be just expanding a shape from its own center, so it's just expanding out like that. But also you might have something like this where that's not where you're expanding from. You're expanding from this point, and everything is expanding out from that direction. Or you could view it as almost like you're at that point and you're shining a spotlight at that shape, and the bigger shape is almost like a uh, a shadow of that. Or another way of looking at it would be like, yeah, you're standing at that point and you're looking at the shape, and it's like, how big a shape would have to be for it to appear like the same size. Like, you imagine like holding a 2 pence coin like right in front of your face. You could make it appear the same size as a car that is, far away because of that perspective. So if you're doing anything in like realistic art or graphics design and things like that, like this kind of stuff, perspective is really important. So you imagine if you were standing at that point, these two shapes would look the same because those lines essentially represent your lines of sight, and you see how they line up perfectly with these two shapes. The bigger shape would be hidden behind that smaller shape that's closer to you. So that's kind of how that works. So the center of enlargement, and you're scaling out from there. So you can kind of draw, if you've got two shapes, or say if we just had that first shape, we could draw the lines out from there, and then we could determine, what shape is, like at what position would the shape have to be that would appear twice as big, need to be twice as big to appear the same size, or vice versa. You could go closer like this, and you'd get this shape. So you see that width of one between those two lines at the bottom. We can then draw in the rest of the cuboid, and you see the vertices line up. And this is one that's then half the size. And so you'll see the surface area will then be a quarter of size, and the volume will be 1/8 of the size as that first shape that we had. So that's scaling. Scaling can be slightly trickier, but I'm hoping that's made things clear. So let's look at reflection. A reflection is another type of transformation. So we have a shape like this, a little triangle, and we're drawing a line like this, and we want to draw the reflection in this line. So a lot of the time we will get like just horizontal or vertical lines. But regardless of what the line is, it's going to work in the same way. Like it's going to reflect like this. Like take each point of that triangle, and you draw lines perpendicular through our mirror here. And the distances to that mirror is going to be how far away it's going to look on the other side of the mirror. And so that's why sometimes when you look at something in a mirror, it can then almost look, really far away. It's like twice the distance of the mirror away. Um, so something like this, you can always get a good idea of this. Like imagine if you had like a mirror on a table and like facing upwards, and you have a table in front of it, and you could always create shapes and put them in front of the mirror and sort of see how they reflect in the mirror to kind of get a good idea of how this works. But mathematically, this is kind of what's going on. Is those distances from each of those points is going to be the same on the other side of the mirror, so that we can determine where that reflection is. And you can imagine sort of taking this paper here, and if you fold it along that line, one shape would go onto the other. Maybe you can see that, maybe you can't. So that's how we would work that out. And you might notice there's a sort of kind of pattern here. Like when we're looking at trying to transform a shape, typically it's easier to just look at a point and see how that transforms. And it's like, okay, maybe we need to look at another point and see how that transforms, and so on until we get enough points that we can see, okay, right, we can now see how the shape is going to change as a whole. And so, yeah, don't look at the shape as a whole, look at points. Uh, Particularly like vertices, those are like important points. You don't just pick a random point, you pick like the important ones. Um, so another thing with reflection, we might be doing it on an axis like this. So say if we've got a shape like this, a little funny circle with a slice cut out of it, and maybe we're trying to reflect in this line like this. again, it's going to be the same thing where we draw perpendicular lines through that line of reflection. When you're doing things on graph, you only really get like horizontal or vertical ones, because diagonal ones can be a bit trickier. Um, and say if you look at the coordinates of these points, you can see how they're going to transform. So you see those points at 8, 3 and 7, 2. It will transform to here because you see 8, 3. So we're reflecting in the y direction, so it's only the y coordinate that's going to change. And you see 3 is 1 below 4. It's now going to go to 1 above 4, which is 5. And likewise, of that other coordinate where the y is at 2, like 7, 2, the y coordinate is 2. If we reflect it in the line, it's 2 below 4. So it's now going to go up to 2 above 4. And so it goes to 7, 6. So you can kind of see how that's going to occur once you understand how the reflection occurs point by point. If we do enough points, we can then get an idea of how the shape as a whole is going to work. And you might get something like this, where you might get a shape that is on the reflection line. Something like this is essentially going to flip upside down if we reflect it in that line. So the same thing applies if something's on the reflection line. This is a relatively basic one. Sometimes you might get one that's not so obvious, but it's going to work in the same way. Whatever point is on one side, it's going to go through the mirror onto the other side. So, okay, you're going to have a mix of points. Some on the top side, some on the bottom side. Those are going to go up and these ones are going to go down. And so it works the same. You're just kind of doing it in both directions at once. So that's something to be mindful of with a reflection. So let's look at rotation. So another transformation uh, is just simply this. When you rotate a shape round, that's if I'm rotating it round its own center. Uh, and we have a thing known as rotational symmetry as well. So just like with the symmetry of that triangle we saw first, where it's like if you fold along the line of symmetry, the triangle comes and lays on top of itself, the reflection. It's kind of like the same thing here. And you imagine when you rotate a shape, when does it land on top of itself again? And this one here, if we do a full rotation of this hexagon, you can see there's several points where it then lands on top of itself. And it'll do that 6 times. And this is the same for any regular pentagon. Any regular polygon. Its rotational symmetry will equal to the number of sides or the number of points it has. So for a hexagon, it's 6. If it was I don't know, decagon, it would have a rotational symmetry of 10 and so on and so forth. Other more complex shapes might not be so obvious. And you just need to sort of try and imagine visualizing that rotation and when will it land on top of itself again. A lot of shapes won't really have much of a rotational symmetry. There's other rotations we could do, like say rotation around a point. Like we saw a simple example of that at the start. So say if we're trying to do this on an axis and we're trying to rotate 90 degrees clockwise around this point, how would we do that? Again, don't worry about the shape as a whole. Look at individual points. So say if we look at this point here and we want to see, this one's an easy one to start off with because it's directly above the pivot point that we're rotating around. Likewise, if you had one that was directly horizontal to it, that would also be a good one to start off with. So we see that one, and if we're rotating around this point, you're essentially moving around this circle. So you imagine drawing like a line to that point, and then you're rotating around. It's going to go like a compass. It's going to go round like that. And so if we're rotating 90 degrees, it's going to go to here. That's going to be the rotation that we have from that point. We can take another point like this one. Again, another one that's just directly above the pivot, so it'll be nice and easy. And that's going to rotate round like this. If we draw a circle around the pivot, it's going to go around like that. Now, with one like this, is a bit trickier because it's not directly above the pivot. But what we could do is split it up into its horizontal and vertical components, especially when we're only rotating by 90 degrees, which is not too bad, because that horizontal part is going to turn into a vertical part, and that vertical part will turn into a horizontal part. So we can kind of see how that's going to rotate like that. And so it would actually do this, going to that point. And so now that we've got 3 points, you might be able to see now how that shape is going to rotate. So if we rotate it as a whole, it's going to go like that, 90 degrees. And so here, this allows us to be using, an actual accurate coordinate system. And, we have like a pencil and a compass. We can essentially draw circles to see how each point is going to rotate. And again, like what I'm always saying, forget about the shape, focus on specific points. That makes it so much easier. And once you get enough points, you can then see how the shape is going to move. Um, so those are all our transformations really that we need to be familiar with. So let's take a look at spatial reasoning. So first of all, what is spatial reasoning and how do we develop that? So um, spatial reasoning is your ability to sort of visualize and understand spaces and shapes and how they occupy that space in your mind. And where sometimes when a shape is going to transform, you can visualize in your mind how, like maybe that triangle we saw earlier and how it reflects. Maybe you could just see that, maybe you couldn't. Same thing with the rotation. Maybe you can kind of just see how that hexagon was going to move around, or maybe you can't. So we need to see how can we develop that skill. Um, So there are resources online you could use. So certainly with three-dimensional shapes, those are the ones that tend to be trickiest to understand because there's only so well that I can show a three-dimensional shape on a two-dimensional screen. Not to mention, even in real life, a three-dimensional shape, you can't see the whole shape all at once, can you? You can only see like the front face, and then you'd have to rotate it to see the back. And so they generally tend to be harder. Uh, there's various online resources, apps, sites where you can, make three-dimensional shapes and manipulate them on the screen. One I often use is GeoGebra, which is a good one. Uh, but for many, it might be effective working with real physical objects. So here's a couple of things you could do to help build this skill. Like Lego is a good one. You could build all kinds of shapes, regular shapes, irregular shapes, and then rotate them and observe them from different perspectives. Origami, which can help develop understanding of symmetries and transformations, where you take a paper and you fold it in different ways, and it's going to transform into something else. Knitting and crochet, another one. So you can study sort of patterns and symmetries in those patterns that you're creating, and tessellation, which is another concept that we're going to look at soon enough, where it's like a repeating pattern. Or if you fancy a bit more of a challenge, you can do twisty puzzles, like one of the most famous one being the Rubik's cubes, where you can understand like rotations and this concept of invariance. Again, another thing we're going to look at soon. Um, so, but there are some that are easier than others. They don't have to be, Rubik's cube is very challenging. There's other twisty puzzles that are easier. So yeah, here's a bunch of examples, from sort of easy to hard, like that you could do to help build up these spatial reasoning skills. If this is something you find difficult, actually visualizing things like this. Right, so let's look at some concepts to do with spatial reasoning, like congruence. Congruence basically means you have two shapes that are essentially the same shape, but they've just been, translated, rotated, or reflected. Um, but they're essentially the same shape. So let's look at an example here of a triangle, and I've got a bunch of other shapes here, and these are all congruent shapes because you might be able to see they're essentially the same shape. So that one in the bottom left is the same shape, it's just been translated some distance. The one in the top right, it's the same shape, it's been translated some distance and rotated. And then finally, that one in the bottom right is a bit more complicated. It's been translated, it's been rotated, but it's also been reflected. But you can see it's still the same shape. Now, examples of things that would be not congruent. So, okay, if I take a bunch of copies of this triangle, so when we're scaling something, it's important we're scaling in all directions. When I scale just say horizontally like this on that bottom left triangle, that's more like squashing and stretching. It's not scaling. Scaling is like out in all directions. This I'm going just horizontally. Or with the other triangle in the bottom right there, say if I stretch it vertically. Again, you can see how it's fundamentally changing the shape. And the last one, an obvious one, would be say if I created a new point, and here I've completely changed the shape. It's not even a triangle anymore, so that's obviously not congruent. So things like that fundamentally change the shape. You're not just moving it, rotating it, whatever. Those would be not congruent. So let's look at similarity, which is like congruence, but it allows a bit more flexibility. So it's the same thing as congruence, but it allows for scaling. So you can you can translate a shape, you can rotate a shape, you can reflect the shape, and you can also um, scale it. So say here, like if we're having a pentagon, again, remember if we stretch it horizontally like that, or we stretch it vertically like that, you're fundamentally changing the shape. But if I scale in all directions, you can see it's the same shape, the properties are all the same, all the angles are the same, but the lengths aren't going to be the same. But the angles are. You've just made it bigger. And so that would be those two pentagons, that first one and this bigger one, would be cast as similar shapes. So similar is not just like a descriptive word in math, it actually has a strict definition. Here's a common example of a problem you would encounter with similar shapes. It's like here, if you have a triangle and then we have one that is scaled up like this, and then you overlap them like this. And so it looks like you've just got one big triangle with a line cut through it, but it's actually like two triangles, a smaller one and then a scaled up bigger one that are overlaid on one another. And these two lines are then going to be parallel. You'll also find these angles are all going to be the same because they're. You remember we did in trigonometry when you scale a shape like a triangle, say up and down, the angles don't change. Uh, and so this top angle is obviously going to be the same as well because otherwise it wouldn't overlap properly. So this is key properties that you need to be aware of. And this kind of scenario with a triangle over another triangle like this is such a common type of question that I see. So make sure you're comfortable with this and you understand why that is the way it is. Let's look at another concept, which is variance. So variance is when something varies. Invariance is then, okay, if it doesn't vary. So when a shape undergoes some transformation, some properties might change, others don't. So if we're working in a coordinate system, maybe we're interested in the positions of the points, of the vertices. We're always going to be interested in the lengths and the angles. So a property that remains unchanged is what's known as invariant under that transformation. But a key thing is that a property that remains invariant under one transformation won't necessarily be invariant under another. So let's do a coordinate system here and look at an example like with a triangle here. If I put a pivot point here and I'm going to rotate around that point, notice that all the points are going to change except for that point at the pivot point. That will stay the same. So that's invariant. It's staying in the same position. Uh, Obviously, the angles and the sides of the triangle are staying the same because we're not actually changing the shape. We're just rotating it round. But you see all the positions are going to change. So the coordinates are not invariant. Take something like this. And if we do, like, say, a translation, if we move it again, all the positions are going to change. But you see the angles and the sides are invariant under a translation. Here, so those ones might be bit more obvious, but say if we take something like this, like we've got a trapezium and we expand it like this. So you can see the side length change, the coordinates have changed, but what we know, angles don't change, do they? So angles are invariant under scaling. But if you take something like a square here, and I'm not going to scale it, I'm going to stretch it horizontally like this. You see the angles in this case don't change. So sometimes you have something like that, even though in general angles would change if you stretch it, but in this case they don't. It's just lucky because it's a rectangle. And you see that the horizontal side lengths have changed, but the vertical ones have remained invariant. Uh, or you could do finally say something like a reflection. If I reflect in that line, you see that line of the rectangle that is in contact with the reflection point is going to hasn't moved. It stays the same. Uh, so that line would be invariant under that transformation of a rotation. So the whole importance of invariance is it can help us simplify things. Like imagine if I was doing something where I'm I've got a shape with some angles and I do a translation and then I rotate it and then I do scaling, then I do another translation, I do another rotation, then finally one more scaling. Like there could be a whole bunch of things going on and I want to work out what are the angles in that final shape. Well, I know the angles are all going to be the same because scaling, uh, translations, and rotations, none of those change the angles in the shape. And same thing with other properties, say like the sides of a triangle of a shape. If I was to translate, if I was to rotate, if I was to reflect, I know under all those rotations, the side lengths are not going to change. They're invariant, and so therefore I can use that information to. But I don't have to bother calculating the side lengths of that new shape. I know it's going to be the same. So that's kind of the importance of invariance there. Is it can help us simplify things. Now, tessellation, we don't do much on tessellation. It's just important to be aware of what it is. So it's when you take one or more shapes and you kind of connect them together in such a way where we don't leave any gaps. They perfectly fit together. And we use this for patterns. You might see this a lot in patterns on like a public pathway or in your kitchen tiles or something. Um, so any regular polygon will be able to tessellate with itself, but there are other more complex tessellations we can create with multiple shapes, and you could just repeat this pattern forever. So say if I take a more complex one here, like a pentagon, not a pentagon, a hexagon, and a square and a triangle, and they've all got the same side length, so they're all just regular shapes, which they kind of need to be really for this to work normally. Um, you could then put a bunch of squares around this hexagon like this. Using a bit of trigonometry, you could find out that these triangles would actually fit in there. And so therefore we could put a bunch of squares around here because they're going to have the same side length. And again, with a bit of trigonometry, you'll find that hexagons will fit in those spaces as well. And you can see now we could actually repeat this pattern, putting squares around those why do I keep saying pentagons? Putting squares around those hexagons and then fitting triangles between those squares and so on. And so this would be like a pattern that would repeat forever. This is an example of a tessellation. Right. So that's enough about that. Let's move on to projections. So projections is basically like trying to look at a three-dimensional shape from various perspectives. So say if we have something like this, I've got a block and I put on a series of other blocks around it, and I want to view this from various perspectives. Like I'm looking at it from the front, from the left, from the right, and then from the top. And typically we won't look from the bottom. These are the directions we'll look at. And we need to see, what is this going to look like? So when you're looking just flat on at one of these objects, it's going to almost look like a two-dimensional shape. Um, and we need to see, what is that two-dimensional shape going to look like? So there's a various shapes that this could take on, and we can see this first one is going to be what it would look like from the left. So again, this is one of those things that takes a bit of that spatial reasoning skill. You need to be able to see this object in your mind and to be able to walk around to the left and look at it left on. What would you see? And you'd see this L shape. If you looked at it from the right, you'd see this other L shape kind of going down and to the left. If you looked at it from the top, you would see, no, so we just kind of like, we're peeking up and looking over the top, you would see this kind of L shape. So even though it's kind of like the same shape, it's like in a different orientation. Um, and finally, from the front, you would actually see the same thing as you're seeing from the left, wouldn't it? So you're looking at it face on at the front, you're going to see a block, block, block like this. So again, yeah, like I was saying, it's hard to really teach this. This is one of those things you want to develop that spatial reasoning skills. Like say with a physical object would be great. Like if this is something you really struggle with, I would recommend even buying some Lego if you don't have some available to you, and you can make blocks like this. Particularly say with this next example, again, if we have a block and then we build up on it and we're using various colors this time, you could make something like this out of Lego and then try and predict what it's going to look like from various sides. And then you can physically pick up the object and look from the right, from the left, look up top and see what does it look like. And you could then check if you're right and gradually build up this ability to see something in your mind. Like some people often need those real world experiences to draw on. Um, so if we look again from the front, left, right, top, you can see from the left, it would look like this. So you look around from the right, the left hand side, you can see the green is going to be on the far left. Then you've got this purple bit, and then yellow and blue on the top. And you wouldn't be able to see the red because the red is behind the shape from your perspective, looking from the left. If we look from the top, we're going to see it like this. So you can see the blue, the yellow, the green, and the red to the right, and you wouldn't be able to see the purples because they're below the yellow and the blue. From the front, it would look like this, wouldn't it? So you've seen blue, purple, purple, red. And you wouldn't be able to see the yellow because it's behind the blue. You wouldn't be able to see the green because it's behind the purple. And finally, from the right, you would get something like this. So you can see most of the shape at this point, except for that one purple that's behind the red. Um, so there you go. That's projections. So now let's look quickly at transformations of graphs. So So we're applying these concepts of transformations now to graphs and functions, which can often be quite tricky, but I'm hoping I can make this simpler. So say if we've got a graph like this, y equals f of x. We don't know what exactly this function is. You can tell it's going to be linear, and we've got 2 points there where it intersects the x and y axis. You could find the equation of this graph if you wanted to. Um, but we're just looking at how it transforms. So say if we've got y equals some function of x, what happens if we add some value to that f of x? Like here, if we add 8, what happens is it ends up shifting the entire graph up by some constant value, that 8 basically. So you can see it there most clearly on the y-axis where 4 goes up to 12. And that's going to be the same for all points along those graphs. So what we're basically creating there is parallel lines. So, and the reason why that is, because think about it, y was equal to f of x. Now we're plotting y equals f of x plus 8. So all the y values have increased by 8. So it makes sense the whole thing will just shift up by 8. So that's an example of a transformation. This is like a translation, essentially, because we're just moving the graph. Here would be an example of a scaling. So here we're doing 2 times f of x. So we had f of x before, y equals f of x. Now y equals 2 lots of f of x. So it makes sense. All the y values have doubled. So you see there, again, on the y-axis, you can see 4 goes up to 8. And so we have this distance here and this distance here. You can see the distances between the graph is going to scale up over, as you go across as well. So you get something like this. Finally, ones like this are a little bit trickier. So what's going on? So we know what a function is. A function is like a series of operations that is happening to, produce an output, like our y values, which are your output. And so when we have something like f of x plus 8, it's relatively intuitive because your f of x is doing a bunch of operations, and then you're just adding one more. You're just doing the operation of plus 8. And same thing with the 2f of x. You're doing a bunch of operations in f, and then you're doing one more operation. You're just times them by 2. Whereas when we have something like this, like f of x minus 12, that minus 12 is acting on the input, not the output. So each input we're putting in, rather than putting in x, you're putting in x minus 12. So so reading from left to right, I like to think of it in terms of like time. So if we're putting in x minus 12, we're putting in the point 12 behind x. It's like you're going to take 12 longer to get to the same y value. And so you think about it, it's going to have an effect of shifting the graph to the right. So the fact that we're subtracting 12 from the x, you would think intuitively that it's going to move minus 12 in the x direction, but it doesn't. It actually goes plus 12. And that's the reason why. Because you think about it, we know that x equals minus 8 gets a value of y equals 0 for y equals f of x. Okay, if we've now got x minus 12, we now need our x value to be 12 bigger in order to hit that value of minus 8 and get the same output of 0. So we would have to put in the value of 4. So 4 minus 12 would equal to minus 8. And so then f of minus 8 is 0. And so that's why you see on that x-axis, the root of this, the gray one, which is our original f of x, and the green one, it's 12 along to the right. So that's kind of the way to think about it. So, or you could just, or you just remember like when you're dealing with the inputs, it kind of has the opposite effect. So subtracting 12 from the input actually has the effect of shifting it 12 to the right, not left. And we get a similar thing as before, like we've shifted it across 12, and that's the same for all points. So we essentially create parallel lines again. And if we have something like this, we're scaling in the x direction, but again, it's counterintuitive. We're dividing the x by 3. It actually has the effect of scaling the x by a factor of 3. So you see here, as we go from left to right, the difference in x is actually getting bigger. Because all the inputs are essentially getting divided by 3. And so if you think of it in terms of a gradient, which is difference in y over difference in x, if we're dividing like we're making the x in the x direction, or all the distances, again, 3 times bigger, then the difference in x between 2 points is going to be 3 times bigger. And so you see in that fraction, the denominator is going to be 3 times bigger. And so the gradient overall is going to be 3 times smaller because you're dividing by a number 3 times as big. And so it makes sense that the gradient that was like this before now becomes more shallow. So you can kind of think of it like that as well. Um, but yeah, just remember when you're acting on the input, it's kind of counterintuitive. It does the opposite. So subtracting 12 actually shifts positive 12. Dividing by 3 actually scales the x values by positive 3. And that's what I find people tend to find tricky. So hopefully that makes sense why that is. If it doesn't, then at least you understand what to do in these cases. So say if we look at a more complicated case. So say if now we're trying to compound these transformations. So say if we have something like this, we do, we've got a quadratic, and we can do the same thing with a quadratic now. So you see 2f of x, we're scaling in the y direction. So from y equals 0, which is at the x-axis, above the line is going to be stretched up, below the line is going to be stretched down. And so you see how it gets this kind of shape. See, this gets stretched up, that gets stretched down like that. If we now do another transformation, so we've done 2f of x, and now we're doing a shift on the x value. So we're adding 10, and you see, okay, from the blue to the purple, it's now going to shift 10 to the left. Remember, it does like the opposite. Um, and so that horizontal distance across the entire graph is going to be the same because all points are getting shifted by that 10. And finally, now we take that transformation and we add 6 to it. And so we know that's basically shifting the whole graph up like this. And again, even though it looks like the graph gets very close in places, that vertical distance is still the same across the entire graph. It's just a bit of an optical illusion. But if we focus on the vertical distance, it's actually the same. And so this transformation here, y equals 2f of x plus 10 plus 6, that's what we need to do. We need to break it down into various smaller transformations to work out what that would look like. And you need to be careful of order of operations of what's going on inside the bracket and what's going on outside the bracket. Inside the bracket, we just have x plus 10. So there's just one transformation. But outside, we're timesing by 2 and we're adding 6. But be mindful here that we've multiplied by 2 and then we've added 6. If we add 6 first and then multiply by 2, that would be a different transformation because the 6 would also get multiplied by 2. So it'd become like, plus 12. So but just be mindful of that. Order of operations are still occurring, but we've got kind of two different things going on. What's going on in the inside the bracket that affects the x, and then what's going on outside the function, which is affecting the y. So, okay, one last example. So say if you've got something like this, and we've got the key points, we see where it's intersecting the x and y axis, and we've got a turning point as well at the bottom. How would this transform? What we do, we've got to break this transformations down into pieces. So first of all, I'm gonna focus on the harder ones first. So the 2x, like we were saying, 2x is not going to have the effect of stretching it in the x direction. It's going to squash it. And so we see where is x0, which is at the y-axis, and everything is going to get squashed towards the x-axis like this. And you can see the x-coordinate, which was 10 before, has gone down to 5. It's gone down by a factor of 2. Then if we subtract 7 from that, again, it's going to move the graph in the x direction, but it's not -7, it's going to be +7 because it's acting on the input. And so 5 goes up to 12 on the x coordinate of that turning point. So we're tracking where that turning point goes. And if we now add 10, that's acting outside the bracket. So that's acting on the y, and that will work in the intuitive way. So you see how it goes from -6, it goes up to +4. And so you see how we can see where those points transform, particularly that turning point is what we're interested in here, because this is how, remember I mentioned before how with a quadratic we could complete the square on it, and by rearranging it you see how we could read off the x, like say if you have completing the square, so it's x, y equals x minus a squared in brackets, and then plus b, you would find the turning point is going to be ab, because the turning point of just original graph y equals x squared is 0, 0. And you notice that completing the square form, what you're basically doing is a translation in the x direction and the y direction. And so that's going to move that turning point from 0, 0 to the point A, B, in the general case like that. So if you had the complete the square form of y equals x minus 3 squared plus 12, the turning point there would be 312. So you might want to go back and take a look at that now. Now that you have this understanding of transformations of the graph, you'd be able to understand why that turning point is what it is. So that's that. That's transformations of geometric shapes and graphs. So did you know that there's a common use of transformations that we're actually using every day? Every time you send a text message, a phone call, anything that requires sending a signal out across the world. Um, and that's this thing here. It's like when you have a signal, like hit that red signal on the left, which is represented like a wave, that can be broken down into various waves, like sine waves, like what we're seeing there in the middle. And then if you project that in the right direction, like you imagine viewing it in that direction, you're going to see these like peaks at particular points. This is an example of what's known as a Fourier transform. And it's like you're taking that signal and you transform it into its various components, and then you view those components from a different perspective. This is something that's being done all the time, which allows us to send signals out and they don't interfere with one another. Like we can separate out different parts. If you're interested in anything like that, like anything to do with communications or radio signals, maybe you want to work with that in the future as your career, this is something you're almost certainly going to come across. Fourier transforms. They're so important. So, yeah, you might want to do some reading on that if you're interested. But that's a real life example of Fourier transforms that we use every day. So, here is our takeaways for today's lesson. Checklist, make sure you understand everything that you need to understand. Next time, we're going to move on to circle theorems. Again, another topic that a lot of people can find quite tricky. Particularly because it tends to require a lot of proof style questions, like prove this thing is true. And that can be tricky for some people. So we're going to see how we can deal with that. So yeah, I will see you next time for circle theorems.